Hello and welcome to Nerdy Nisa. Today we're going to be going through galvanic cells, otherwise known as Daniell cells. We're going to be going through what they are and then how they work. Firstly, on what they are. What is a galvanic cell? It's essentially a cell that takes advantage of a spontaneous reaction. It takes advantage of reactions that happen instantly as soon as two substances come into contact. So, reactions that are generally exothermic and releasing energy. So, what scientists realized is as these reactions are releasing energy, like copper ions and zinc metal that spontaneously reacts, they can actually harness that energy and convert it into something useful. They can take that chemical energy and they can convert it into electrical energy. And that's essentially what you see happening in a galvanic cell. Now, when studying galvanic cells, this is probably the image you're used to. You're probably used to the two beakers and the weird tubey thing between it that you've seen in your textbooks, and it's all a bit jarring. So we're going to take it down to its basics. And we're going to start exactly where the scientists started, at the reaction itself. So let's imagine we had the same example as above. We had my copper 2 plus ions and my zinc metal. We know that these are going to spontaneously react with one another. So if I want them to react, I'm going to need to put them somewhere. Let's imagine that I've got some copper ions over here in some sort of aqueous solution. We can make it a nitrate solution because those don't form precipitate. So those are pretty good ones because that means we don't have to worry about any precipitate forming. So I've got my copper ions over there, and over here I can put my zinc metal as an electrode. Now, the general way we imagine these spontaneous reactions happening is that the electron moves directly from one species to the other. It's kind of different in a galvanic cell because you've got this intermediary, you've got this metal wire. The electrons are going to move from the zinc through the electrical wire all the way down to this electrode to then go and reduce the copper. So it's still a spontaneous reaction. It's still between the two, even though they don't come into contact. It's just that there's an intermediary that is allowing my electrons to travel from one to the other. So the way my electrons are going to travel is they're going to travel from my zinc. They're going to go all the way down to my copper electrode. That's my electron movement. Now, what do my two half reactions look like? I've got my copper that's gaining 2 electrons to become copper metal, and my zinc, which is losing 2 electrons to become zinc 2 plus. So the way that then looks on my diagram is I've got my copper, which is yanking off the electrons that zinc is sending down. You see it reducing and gaining those electrons so that it can form nicely on this electrode. That's the reason that we put this electrode as being a copper electrode in most galvanic cells, so that we can allow it to get thicker, as that copper has a place to go and it has a place to form around. So it's not just like forming and gathering at the bottom of the beaker. We want it to form nicely. So that's the reason that we have that copper electrode there, and it's the reason that electrode is going to get thicker throughout the reaction. Now, on the other side, what you're going to see happen is the zinc losing electrons. So that's going to form a whole bunch of zinc ions. Now, that's the reason that we have a beaker on this side as well. It's because we don't want these zinc ions to just be like lying on the floor, so we want something to catch it. So we can make this like a zinc sulfate solution if you like, just for a bit of variety from the nitrates. So that essentially gives us understanding as to why, even though it's only really this zinc metal and the copper ions reacting, you still have a copper metal over here as an electrode and a bunch of zinc solution in the other beaker. Now we can label these two electrodes, right? Over here we have our reduction taking place because copper is gaining electrons. So this over here is our cathode. And on the other side, we have our oxidation taking place. So this over here is my anode. So that's the basic idea. You have electrons moving from one side to the other. And then what you can do if you want to harness this electricity is you can put like a light bulb in between on this wire so that you can kind of gather those electrons, use them as they're passing through. So use them as they're on their way. That's the basic idea. But they realize that you kind of run into a problem if you just allow this to happen alone. Because the problem is that, as you can see, this electrode with my zinc and this beaker over here is becoming increasingly positive because it's just losing so many electrons. And this beaker over here is becoming increasingly negative because it's gaining so many electrons. Now that creates some complications. Because if this beaker over here is super positive, then my electrons that are supposed to leave zinc and travel down the wire aren't going to want to do that. Because now the beaker is so positive that my electrons over here are now getting stressed. Do they go up or do they go down? They're being attracted in both ways. So they're just no longer going to travel down the wire. The reaction's going to stop. And even if they did want to travel down the wire, they'd be so repulsed by the negative side and the negative sign in the other beaker that they no longer want to even go near that cathode. So that becomes the problem. We just have two charged beakers, which interferes with my reaction. So the solution that we have and the solution that we found out is to create a salt bridge. Now this salt bridge over here is something that's made out of really any salt. We generally use potassium nitrate and sodium nitrate because they're really soluble, they don't react with things, they're just like a really good combo, right? So you're going to use a nice concentrated solution. Let's just use sodium nitrate for this example. Now a sodium nitrate aqueous solution is comprised of sodium ions and nitrate ions. And what happens is, because my sodium ions are positive and my nitrate ions are negative, my sodium ions are going to go all the way down into my negative beaker because they're positively charged, so they're going to attract there. More positive charges entering that negative beaker is going to make my charge neutral. So I'm no longer going to have a charged beaker which no longer repulses the electrons. And the similar thing happens on the other side. I have my nitrate ion which is negative, so it gets attracted all the way down into this beaker. With more negative charges entering it, I no longer have a positive charge. So my electrons are no longer attracted back into the beaker, so they're no longer conflicted. And that's essentially why we have that salt bridge, to neutralize those beakers and complete the circuit, to ensure that we don't have electrons that get really confused as to where to go. So in summary, the way a galvanic cell works is it uses that spontaneous reaction and that electron transfer to intercept and place something there so that we can use it for electrical conductivity. So just allow those electrons to pass through something if we already know there's electron movement. And then we have a salt bridge to ensure that both beakers stay neutral throughout the reaction. I hope that this video helped young scientists. If not, and you have any questions, please leave them in the comment section down below.